right, let's get started. Welcome, everybody. Thank you for coming so many in this morning, despite the last-minute rescheduling of this talk. My name is Nicolas Melot. I'm Director of AI Research at Unity Labs. This will be a joint presentation with Vincent-Pierre Berges, Senior ML Engineer at Unity Technologies, Robin Nilsson, co-founder at Carey Castle, and Mantas Puida, which is ML Engineer at Unity Labs. And today we're going to talk about generating behaviors, game behaviors, using AI and machine learning in Unity. So first, a little introduction slide. What are we going to talk about? What are we talking about when we say game behaviors? So obviously we are thinking of powering up NPCs, squad of NPCs. Another obvious application would be to create AI opponents. But there is more. We can think also of storytelling engine, the behavior of the world, the behavior of your game world, the actions, the game event that happen to drive the story. We can be thinking of smart assets. In another project, we are working about adding semantic tags to objects so that they can be involved in behaviors. We're also talking about various types of player advisors. And also, we will talk a little bit about application to game testing. So this is not an exhaustive list. And this is also roughly what usually falls under the name Game AI. So it's a talk about Game AI. And we're going to present you two new tools for Game AI in Unity. OK, so when we want to generate a behavior, at this stage in the history of AI, we have three types of approaches. The first approach, you're going to code your behavior. You're going to explicitly encode the reaction of your agents depending on the inputs he receives. You can do that in a C# script, and you can do that using a state machine, a behavior tree, a rule-based system. All of these are just visual behavior programming language. The second approach you can use when you want to derive a behavior in a game is by solving a problem. So think of navigation and using nav mesh. Here you want to create a behavior of locomotion in your world. You don't write a state machine. You don't write a behavior tree. You're going to use a navigation engine which creates a model, solve this model for the shortest path, and then you take the first action of the shortest path and you call that your decision. This is an example when you make decision and generate behaviors by solving a problem. Okay. Finally, the last approach, very famous nowadays, is machine learning. You can also learn your behavior. You can learn it from data or from experience. If you learn it from data, you could, for instance, imitate a human player. And in reinforcement learning, we are able to learn a behavior just by interaction with the game and by providing reward to the agent when he does well and punishment when he does bad. Okay, so most of the current practice in Game AI is to actually code the AI. There are reasons behind that. There are problems of controllability, authorship. We don't say it's bad, but we want to propose you also different approaches. Actually, we really believe in Unity that to solve most of complex Game AI problems, you need a little bit of three approaches. So today we're going to present two new tools. The first one is called the AI Planner. And it shows you how to generate behaviors by solving a problem. The second tool we're going to be talking about is the Machine Learning Agents Toolkit. That will be the second part of the talk. And it's an approach to generate behaviors with machine learning. If you want to hear a little bit more about Game AI and what we think at Unity, I invite you to check our talks. For instance, at Unite Shanghai this year, or Unite Seoul, or at GDC, where we spend a little bit more time. But now, let me dive into the first part, the AI Planner. OK. So, as I told you, the AI Planner is a general tool to author behavior. You will generate behavior in your game by solving a problem, not by coding the behavior. So what does it mean to solve? What is the basic principle we're going to use for solving a problem? Well, this principle is called search, state space search. And you know it very well if you have been doing game AI, because this is what you do in every navigation system. You create a representation, you search it, and you get a behavior. This is true so for navigation, this is true for motion planning. And I'm going to show you how you can use that in general for any kind of behavior, actually. So what we're going to do, I'm going to show you how to use search in a more complex space. So here is how search works for navigation. When you want to solve a shortest path problem, you would create a representation of your navigation problem, most often as a graph, where every node is a location and every action is a locomotion from one location to the other. Now, if we have a starting state on the left, a goal state on the right, and if we have cost on every navigation action, we can run a shortest path algorithm that will tell us, hey, here is your shortest path to the goal. So we want to generalize this to any kind of behavior. And the key to do that is to increase the information that is encoded into this graphical representation of the problem. We're going to put more information. First, we're going to increase the information contained in the state. Before, the state just contained information about which location the agent was. Now we're going to add more. We're going to say, hey, you are at your starting location. We can put information about its inventory. You are currently carrying the key to your home. We can put information about your resources, your fatigue level, or your fatigue at level 8. Any information which is relevant to my decision making should be put in the state and generalize it. Next thing, we're going to generalize the notion of action. When you're doing navigation, all your actions are locomotion from one location to the other. Now we're going to consider more variety in actions. So we'll still have a navigation, wrong key. We still have a traveling action to navigate. As you can see, it will change the location. We were at start, and now we are at home. It might also impact our resources. You could see, it cost me 1 point of fatigue. So and this gives me to a new state where I'm at home, I still have my key to the home, and my fatigue is now a 9. Now, given I am at home and I have the key to the home, I can consider entering the home using my key. And because we are in a video game, my key is consumed when I use it. So if I enter the home, now I'm in home, no more key, my fatigue is the same. Now I'm at home, I can sleep, resetting my fatigue to 0. And now that I'm fresh, I can go to the goal. So you see, I have states, I have transition between states with cost in green, so I can run a shortest path algorithm. And this shortest path algorithm could possibly tell me, hey, this is the optimal solution. Just first go to the home, take some rest, and then finish your trip. Maybe every attempt to go directly to the goal will lead the agent to die of exhaustion, so this is the optimal solution. So what I just showed you, I just used the shortest path algorithm to create a behavior which contains navigation, using your inventory, replenishing your resources. And it's still shortest path. Okay? So this is the basic principle of this tool, to create a shortest path in a complex problem representation. In practice, the tool comes with a planner, which is a search engine, which is going to represent the problem as a graph like I just showed you, which is going to solve this graph and give you the optimal solution. It comes with a controller, which is monitoring the evolution of the game, querying the planner to get plans, monitoring the execution of the plan, checking if we need to move to the next action because we just completed the one we were doing, checking if the plan has broke because something changed in the world and we need to replan. Okay, this is traditional. A very important feature. At Unity, we're not solving one problem. We're making tools that we hope you can use to as many games as possible. To make this possible, in this tool, we created what we have to define a planning domain, we introduce the notion of planning domain, which is a representation of the particular problem you would want to solve. And to represent this problem, we derive a language, which is called the planning domain language. So you're going to use our planning domain language to define the problem, and then automatically the AI is going to create the graph and search it for you. So most of the rest of the talk is about the language. I'm going to show you how you edit, or you create the problem that the AI automatically solves. So the big idea behind this language that we call the thread-based language is that we should be able to tag the elements of your game to tell to the AI, oh, this object can be involved into this behavior and it will play this role. So for instance, we're going to create a tag called eater, a trait. We're going to create a trait food, and we're going to say to the AI, hey, every eater can eat a food. Then later on, we can just go and tag objects through the world, and the AI will know what's possible. That's basically the idea. The second step is that these tags are not just tagged. They actually contain members containing information which is relevant to the semantic concept they represent. Again, this is something you decide. So you can decide to create a tag eater that will contain a field representing the current hunger of the agent. You can create a tag localized to say that the agent is at a single location in the world at each instant. And then you will create a field saying, oh, my current location is that location. So let's look a little bit closer at this agent eating an apple. The action will take two parameters, two game objects, one with the trait eater, one with the trait food. And we also, in this game, you can eat some food only if you're at the same location. So we also want the eater and the food to have the localized trait. And we want them to be at the same location. So if you have this configuration of things, you're going to be able to apply the action eat, not that the action has parameters, one for the agent, one for the apple. And as a consequence, the apple will be deleted, and the current hunger of the agent will be decreased by the feeding value of the apple. And the agent's location doesn't move. Simple. So this is how this trait is basically how you define the relevant variables of your problem. This is the first part of the language. The second part are the actions. So you define your traits, you define your actions. Let's dive a little bit on how we define an action. So actions have parameters that represent domain objects that are involved in the behavior. So in this case, we will have one parameter for the agent which is going to eat, and one parameter for the object which is going to be eaten. Next, we don't want an action to be executable in every possible state, so we're going to add conditions for the action to be executed. As I mentioned in the previous slide, first we're going to impose some traits. Oh, the eater must be an eater, and it must be localized. The object must be a food, and it must be localized. That's how we put conditions. The first way. The second way to put conditions is actually explicitly using the traits of the object's parameter, we can check that the agent location is equal to the current location. If this is true, we can implement this action. And the consequences of these actions are of three types. Consequences of action can be either the creation or the deletion of an object. It can be the creation or deletion of a trait to an object, or it can be the change of the value of the member field of the traits of the parameter objects. So in this current case, we have two effects. We will decrease the agent's hunger, and we will delay the object. Okay, so let's return a little bit in the talk. I showed you we are going to create a graph. This is how we create a graph. This is a state, a planar state. A planar state is a set of objects with traits attached to them. So that's a possible state. When you have one agent, three locations, the agent is a eater, he's tired, which means he has fatigue and he can sleep. Location is a bed where he can sleep. Another location is a workplace, he can work. Another location is a food source. Now, depending on the state, depending on the state in which we are, some actions will be available. Traveling action will be almost available in this domain. But if we are in a place with a bed, we can sleep. If we are at a food source, we can eat. If we are at a workplace, we can work. And this is how we create this graph. That later we solve. Okay? All right, I have officially 1 minute left. So I'm gonna be over time. And let me go quickly through 4 applications we are developing. First, you can download this planner from the package manager as of today. And you will get the little example, the little orange guy, which is eating, drinking, and working. It's called Auto. To release the package, we are working with Apex Game Tools when we are powering the AI in a new game they are producing, which is called REBOTS. Before working on REBOTS, and we have been using Overcooked from as our benchmark to develop the planner. So lots of thanks to Team 17, Ghost Town Games, and Ghost Town Games for giving us the code of the game. And it was really fun, and I wish we spent more time because there is much more to do with Overcooked. We're also making a cooperation with a company called Guidekick, which is currently developing an application for navigation in airports, and we are increasing to activity planning. So instead of just saying, I want to go there, you're going to say, I want to go there, but on the way, I'd like to buy the news, I'd like to get a coffee. And by the way, it's better if I get the coffee before the news. So general activity planning using this planner. And I like this a lot because it's not an application in gaming, so it's interesting to show that the technology has more width than just game AI. Finally, through a cooperation with Ludia, we are using the planner to do game testing on a match 3 game. And here you can see training. You can see the planner developing the tree. And when it goes slow, it's not because the planner is slow, it's because we're executing the game and the game is slow. Okay, time to wrap up for me. Here is maybe the most important point of all the talk. I'm just presenting you the planner, and I tell you, oh, it's a way to control an NPC so that it solves a problem that you define through the language. But in fact, it's much more. The planner can be seen as much more. First, the trait-based language is a general behavior authoring tool. Remember the idea? You just tag an object to say that this object can be involved in that behavior. It doesn't have to be a planner. It could be a behavior tree. So we're currently working on an implementation of behavior trees that would accept parameters, objects with traits. And in our vision, many of the game AI tools we're going to be developing will be going through that. Next point, the planner is a simulation, is a semantic simulation and query engine. If you have represented your problem, you don't have to use the planner to decide all actions, but you can use it to make questions. What if I do that? Do I have enough resource to do that? And if I get there, what will be my possible actions from there? So you can make semantic queries that you can use also in a behavior tree or any kind of game AI system. And finally, we implemented a fancy search algorithms. And you can use this search algorithm independently of any language elements. So we're just providing you a fancy implementation of MCTS that you can use for your search. Okay, that's about all I have the time to say about the AI planner. So now I'm going to give the mic to Vincent-Pierre Berges. He's going to talk to you about the Unity Machine Learning Agents Toolkit.
All right, thank you, Nicolas. So now that we know that we can use planners to have our machines solve their problems, in this part of the talk, we'll learn that we can have our machines learn from data in order to play games. So first, I want to talk a little bit about the relationship between machine learning and gaming. So in the machine learning community, oftentimes we use games and video games to benchmark, to show the performance of a machine learning algorithm. And oftentimes when there is a breakthrough, we just show a new game that is now we can now beat using machine learning when it was not possible before. So there is a lot that games are currently doing for machine learning, but in this talk, I will talk about how machine learning can be used in games and can help in creating games. So really, this is about how we can teach machines, how machines can learn their behaviors using data, rather than having to code the behavior manually. So we want our agents in the game to use data that they collect by playing the game. So I just mentioned the term agents, and I want to really define what I mean when I talk about agents. And this is a lot of text to basically say that an agent in an environment, in this scenario a video game, is a something in the game that is collecting observations. So this observation are informations that the agent is collecting from the environment, and then agents take actions in the game according to their policy. So here the policy is really a mapping between observations and actions. So it's basically what the agent will do in what situation. And so this policy is defining the behavior of your agents, because this is defining the succession of actions that the agent will be taking in the game. So this was really abstract, so let me go through an example in a shooter game. So an example of observations that an agent could collect in a shooter game is, for example, location information, where is the agent in the game, velocity, how fast the agent is currently going into the game, maybe rotation information, what's the orientation of the agent. We can also have camera observations, so it's just visual input, what is the agent seeing into the game. You can also have ammunition count and maybe some kind of data telling you where is the closest enemy. So then the agent collects all that information, passes it to the policy. The policy here is a neural network. The policy will determine what is the next action to take, and then will give that action to the agent to be performed. So an example of action could be move around, jump, turn if you have to change your orientation, shoot, and maybe duck if you want to dodge something. And then you repeat this cycle. So you collect observations, you run it through the policy, and then you take your action. And it's this repeating process that determines the behavior of your agent. What is the agent doing? So what we're really trying to do here, we're trying to train the policy. We're trying to figure out what is the optimal policy to play this shooter game. So now, how do we create those agents, and how do we train this policy? We have an open source toolkit for this. So this is the Unity Machine Learning Agents toolkit. It's completely open source. You can just download it and start using it now. And it's using the latest advancements in deep learning to allow you to create agents in your game and use deep learning to train their behaviors from data. So how are agents useful in video games? We see three types of applications. So there is the types of agents that are player agents. They play from the point of view of the player. And you can use these agents to test the game and maybe to figure out maybe difficulty balance. Like maybe is my game too hard because even a machine learning algorithm cannot solve it. That will be a problem. You have also non-player agents. So these are things, physical incarnations in the game that will be alongside the player. So they can be enemies, they can be companions, or just characters in the game that the player can interact with that are augmented with machine learning. The third type are invisible agents. And invisible agents, they just control some aspects of the game. So for example, difficulty, and they just tune the experience of the player. Now, I will talk about the toolkit in a little bit more details. So there are 3 steps in order to be able to create intelligent agents in your game using the Machine Learning Agents toolkit. 3 steps. First, you have to integrate the toolkit into the game. Then you go through a training phase where the agent will just play the game, collect data, and try to get better and better at playing the game using that data. And then once the behavior is learned, once the policy has been created, you can take this policy and put it into your game, into your application, embed it into the games, and just deploy them on any platform you want. So first, how do we integrate the machine learning agents toolkit? So this is a rough diagram of how it works. This is an example with just 2 agents and 1 brain. The brain here is basically the policy holder. It's what's holding the policy. And you can see that the agents are connected to a brain. Here they're connected to the same one because we want them to have the same behavior. So what happens is that these agents will, at each time they need, collect observations about the game, give that information to the brain will then take a decision and give to the agent the next action they need to perform. And just repeat that cycle. So here the 2 agents have the same brain, this means they have the same behavior, but that doesn't mean they will always do the same thing at the same time, because they will not be having the same observations. So there are multiple scenarios you can think of. So this is an illustration where you can have 1 brain that has multiple agents connected to it. So here they'll all share the same behaviors, but you can do much more complex things. So here you can have, for example, 3 different types of brains with maybe dogs, cats, and mouses connected to different brains, and just taking their decisions using machine learning all together in the game. Now to talk a little bit about this training for our agents. So there are 2 main algorithms we use to train our agents, to obtain our learned policies. The first one is using reinforcement learning. So in reinforcement learning, what happens is that the agent is just playing the game, like experiencing the simulation, and it learns through experience. So when the agent does something, sometimes it will get a reward, and when it does something bad, sometimes it will get a penalty. And then it learns to optimize its behavior in order to collect as much reward as possible. This can be a very slow process because the agent has to do a lot of trial and error, basically try everything out and figure out where is the reward, like what is good behavior and what is bad behavior. The advantage is that since the agent is interacting with the game alone, it doesn't need any human interaction, you can speed up the simulation a lot. So you can have the agent just run in super fast versions of games, and you can also deploy multiple of these games in order to collect a lot more data and have the agent learn a lot faster. Since there is no human interaction, there is no human telling the agent what is good and what is bad, then the agent will gain superhuman abilities because it's not biased by what a human would do. So let's look at a little example with this demonstration. So this is the chicken crossing the road. Getting a present gets the agent a +1 reward, and getting hit by a car gets it a -1 reward. So this is just right before training. So this is the initial behavior of the agent. You can see it's very chaotic, it's very random. The agent doesn't really know what to do. It doesn't know that cars are bad and that presents are good, but it gets hit by a car and then it gets a penalty. So then after a few hours, you can see that the agent starts to realize that presents are good and is kind of trying to avoid the cars. But he's not very good at it yet. Although it's probably playing better than me already at that stage. And after 6 hours of training, this is using a very slow learning algorithm. You can see the agent is just superhuman, like I don't even know what's going on anymore. Maybe it gets hit by a car, but that was a very difficult situation to be in. It's just racing through the game. Now, the second way to train our agents is using imitation learning. So when you use imitation learning, you provide demonstrations to the agent, and the agent will learn using the demonstrations. This requires you to play the game a little bit from the point of view of the agent in order to collect enough information for the agent to be able to learn. The advantage is that the agent is only mimicking what the human is doing. And this means that this can go pretty fast because the agent doesn't need to learn that presents are good and that cars are bad. It just needs to imitate whatever the human has been doing. Because there is a much stronger signal here. It's much easier and faster to learn from mimicking a behavior. The issue is that you will get more human-like abilities because you're just imitating a human. You're never going to get better than the human that showed you how to play the game. Let's see that with an example here. On the left is a human playing the game, and on the right is a machine trying to imitate. So this just started. This is the beginning of the training, and this is in real time. So you can see the agent is still very bad. It just hits the wall, but there is no notion of the wall is bad. It's just like, what would the human do in that situation? And you can see after 20 seconds, it's already like avoiding the walls. It's already playing fairly well. It's learn to turn right when it turns right and learn to turn left when it turns left. And this is just after a few minutes, so it's extremely fast. The agent just plays roughly at the level of the human that provided the demonstrations. So now there are drawbacks to each of these techniques. So when you're using reinforcement learning, for example, your agent has to explore pretty much everything in order to know what's good and what's bad. And that can take a lot of time. And when you're using imitation learning, you have another problem, is that your agent is never going to get better than the human that showed the demonstrations. And by now you probably know where I'm getting at, is that we should probably combine the two and get the best of both worlds. So when we combine reinforcement learning and imitation learning, what you do is that the agent can learn through experience and demonstrations at the same time. So the agent will use the human demonstration in order to explore better. So it's just like if I show a few demonstrations of the human catching presents and dodging cars, the agent will very quickly be able to imitate that behavior. And then it will use its experience, like the reward signal, like, oh, getting a present is actually very good. Maybe I should do that more. Maybe I should try to get better than the human's demonstrations. So you can, in the end, get better behaviors than the human that originally played the game. And I'm going to show you an example of a game in which the goal is to press a button, knock down a pyramid, and then grab the gold brick at the top of the pyramids. This is the pyramids environment. It's one of the demonstration environments in the repository. And it's a very hard environment to learn on because you don't get a reward immediately. Like, you only get a reward when you are grabbing the final brick, when you're knocking the pyramid and getting the gold brick. So it's very hard to learn with it. After 1 minute of training, you can see that the agent that is using reinforcement learning and imitation is pressing the button already from the get-go, and then is knocking the pyramid down. It's not getting the brick yet because it's just imitating the human. So it just doesn't know that the brick is good. It just knows that the human has been knocking down the pyramid. So it just tries to do that. And after 15 minutes, the agent learned that it must press the button, knock the pyramid, and get the brick, while the agent that was trained only using reinforcement learning is still exploring, is still trying to figure out how things work. And it will probably eventually be able to learn. It will just take a lot more time. So these are all the features that are present in the Unity Machine Learning Agents Toolkit. A few new ones. Now you can use multiple GPUs to accelerate your training. You can also train generalized agents. So this is when you want your environments to have multiple configurations of them, like you want to train your agents on slight variations of your environment, and that allows your agent to generalize better because it's been exposed to many different versions of the same environment, so it will be able to adapt better to newer versions of the same environment. The last two, pre-training and Gale, are the techniques we use to combine reinforcement learning and imitation learning. And now, to talk about their successes, I would like to invite Robin from Carey Castle to talk about their experience integrating the Machine Learning Agents Toolkit with their game.
Thank you very much. Hi everyone, I'm from Carey Castle, a small Swedish game company. We are a small team, but we love technology, and we use it to create great content for our games. I am Robin, and my colleague Per is also here in the audience. Today, I will talk about the machine learning we use in Source of Madness. We use it both to create millions of monsters and also to create a unique visual style painted by AI. But today, I will focus on the monsters that we use ML agents for. Source of Madness is an action roguelite game. As an acolyte from the cult of knowledge, you have to close the box of Pandora and end the madness. You travel through a rich, dynamic world, but every time you die, the whole world changes and you start over from the beginning. In this world, there are a lot of horrible creatures, and every time you play, these are different. So we say we have millions of procedural monsters, but actually it's 5 sextillion combinations if you count all body parts. That would be hard to code by hand, so we use machine learning to control their movement. There are a lot of reasons to love machine learning. The reason we use it for our monsters is that it makes them feel alive. You see how this monster climbs up this ledge by using his muscles controlled by machine learning. It looks very organic and scary, and it really fits the Lovecraftian style in our game. Even if we train the monsters to do one thing, the result gets quite varied and unpredictable. And that variation makes the monsters even more scary, and it surprises the player and makes them more interesting, since you never know what the monster will do next. This is an old video from when we first started to get the machine learning working. These monsters were trained in a static environment, but still they behave very well in a dynamic environment. So after the training, I took this circle and I control it with my mouse. I start to poke them and push them down. And you see how they try to grab the circle, and it looks lifelike. They're trying to defend themselves. And they take this data from the training and they apply it on a new situation, and that is a benefit of machine learning. This is a setup we use for the monsters. So we pass in data about the nearby environment and the state of the monster's body, like how it's bending and moving around. And then the brain takes a decision of how should I control my muscles in the body, and should I grab the ground, it can climb. Then we give a reward to move towards the player. An interesting thing we found is that we can add extra rewards which are smaller, and then we can control to get different types of movement. I will show an example of that now. So these monsters were trained in a very similar setup, but on the left side, we give a small extra reward to stay close to the ground. And you get this rolling behavior, which is pretty fast. And on the right side, they get their extra reward to stay high above the ground. And even if their main goal is the same, to move right, they get a very different way of doing so. And that we can use to create more variation of our AI. We will have a lot of different types of monsters. We're planning for bipeds, quadrupeds, flying monsters, and monsters with a lot of legs. This is a video of how the monsters get better during one training. So they start out pretty random, but they get better after a while. One thing you notice here is that the monsters are randomly put together by different limbs. They are not all having the same body, but we train one brain to understand how to move with almost any body. That took a while to get to work, but it works now. We do one thing to combine scripts with machine learning, because when it comes to movement, we want the machine learning, and that works great. But for attacks, we need certain patterns, certain timings and cooldowns, so that a skilled player can learn to avoid taking damage almost entirely. So you see this punch attack is charging and hitting the player. That is controlled by a script. And when one limb is punching, we just ignore the machine learning for that limb for a while. And in that way, we can get the best of both worlds. Finally, this is how it looks like in the game. So you have this player. The website is sourceofmadness.com if you want to check it out more. And we're also showcasing the game in the Game AI kiosk here at Unity Unite. Next speaker is Mantas, who will talk about how to use the neural nets on a device. Thank you very much.
Thank you. So I will be talking how to embed the brain and neural net you trained in the ML agents right into the device and or the platform you are targeting with your game. And just to quickly remind that single brain can control multiple agents. And what happens inside that brain? Basically, we have here neural net, which has hundreds of thousands of parameters. And to actually execute that brain and make a decision, you need to execute this neural net, which basically runs to the multiplying large matrices. And the more agents you have, the larger the matrices are. Right. So why it's hard to embed the brain in the real-time game engine? Most of the off-the-shelf frameworks for neural nets support only a few platforms, don't play well with the graphics APIs, and also often require platform-specific framework workflows. And to solve all these problems, we created our Unity Inference engine, which allows you to deploy and execute your neural nets in uniform way across all the platforms we support. Yeah, it's built on high-performance Unity tools and technologies such as EL2CPP, burst compiler, compute shaders. It provides single API to interact with the inference engine. Also, it supports both GPU and CPU inference. And my favorite part, it's fully integrated with ML agents, and it's actually shipping with ML agents out of the box. Yeah, let's look at the specific examples. Here we have Corgi, which is controlled by brain trained in ML agents. And its body being controlled directly by that brain, basically it's just moving limbs. And no human-made animations were done for the body of the puppy. And it's trained to fetch the branch and bring it to back. Yeah. So the cuteness is not hard-coded. It's something neural net learned on its own. A single puppy is nice, but swarm of them is much better. Yeah, and now you see it's actually the case when running the inference on the GPU for multiple agents is where GPU inference shines. And we support all the platforms down from the game consoles to the AR devices. Yeah, and we started shipping Unity Inference Engine, which we codenamed Barracuda from the beginning of the year. And we would like to do some small updates, what happened since then, and give some advices how to best use it and what's coming soon. Yeah, so now GPU inference is twice faster than it was at the beginning of the year, and we are testing it against most of the popular networks, including Pix2Pix, VGG, ResNet. And there is a new feature in ML agents that you can use ResNet as the visual decoder for visual inputs of your agents. And it's good news, it's now running twice faster on the device. Also, people are often asking when to use the CPU inference and when to use GPU inference. Typically, CPU inference is having less latency on the device for ML agents models. But when you have visual observations, or large vector observations, or large amount of agents, or large hidden layers in your brain, then switching to the GPU is the best choice. And we have reports from the users that switching from the CPU inference to the GPU improve the performance 10 times. And our big update for performance is 60 times less of the temporary allocations. We achieved that in 2 rounds. We optimized both ML agents and the Barracuda to work together. So in the first round, we improved it 6 times, and next round, another 10 times. hopefully your garbage collector will be happy about that. And it's shipping already. And another nice tip for the performance, if you are using Unity 2018 or later, you could use Burst low-level optimizing compiler for C# and boost your CPU inference up to twice faster. And just you need to install Burst via Unity Package Manager and download Burst plugin for Barracuda and put it in some plugins folder under your project. And often people asking if Barracuda and Unity Inference Engine could be used outside of ML agents. Yes, it can be used, and we support a bunch of popular neural nets like MobileNet, VGG, YOLO, SRGAN, Pix2Pix. And some of them are still not supported, but we are working on that. The usual tip is if your network can be converted to ONNX format, which is open neural net exchange format, then it probably will run in the Barracuda. And what's coming soon? So Barracuda is, and Unity Inference Engine is becoming standalone product, and soon we will have package for Unity Package Manager. Also, we are working on ONNX model imported directly in editor, which means you won't need to use Python scripts anymore, and you can just enjoy your neural nets right in Unity. And we're also working on optimizations for MobileNet, adding DirectML support, Apple Metal Performance shaders, and bunch of popular object detection networks. And that's it. Please point your cameras to the QR code. It has all the additional resources for this session, including the links to the things we talked about. And also, we are waiting for you to come to the Games AI kiosk, where we have great demos, and would love to chat with you. Also, for quick questions right after the session, we can meet outside and talk about Game AI. Thank you.